Okay, so moving on to the next section, we're going to be dealing with logarithms and exponential functions. So just a couple things to remember. Remember, whenever we have a logarithm, and there's no base here, that's going to be base 10. And the main thing we need to understand when we have a logarithm like that, we're trying to evaluate this, right? We want to find the value of this logarithm. So what this is basically asking is you want to take the base. It's saying 10 raised to what number is going to equal this argument, which in this case is going to be 100. So hopefully you understand here that with just a little bit of simple math, we can represent that is going to equal. So therefore, we can say x is going to equal a2. So what I'm going to do is actually move this over here. But that is basically what we're asking. When we're looking at the logarithm, you can kind of sometimes think of a logarithm as in its exponential form. So when I say log base 10 of 100, like what am I asking? Well, I'm saying 10 raised to what number equals 100. So you can see that it is 2. In this case, we're saying 2 raised to what number equals a 32. Well, hopefully you recognize that 2 raised to the second power is 4, 2 to the third power is 8, fourth power is 16. So the fifth power is actually going to be a 32. Okay, now some of these you should hopefully, as you kind of remember going back through there in your head. Once we get into problems like with fractions, that's a lot of times where things can kind of get confusing. That's why I like setting it up in the exponential form. So here I can say 3 to the x, right, is equal to 1 over an 81. But in this case, we don't want to write it as a fraction. What we're going to want to do here is rewrite 81 as with a negative exponent, right? I can rewrite this as 81 raised to the negative first power. Now, what I want to be able to do is also be able to say, well, 3 raised to what number equals 81, right? Because, if I'm trying to say 3 raised to what number, like I got to be able to see what that's going to be to 81, and that might not be apparent to you. So one thing we can kind of recognize here is using what we call the one-to-one property, right? So the one-to-one property basically states is if I have a to the x is equal to a to the y, then x is going to equal y, all right? So we want to get these to be the same base. So 3 raised to what number equals an 81? Well, guess what? That is going to be a 4. So I can say 3 to the fourth power is the same thing as 81, and that's raised to the negative first power. Now using the product rule of exponents, negative 1 times 4 is going to be a negative 4. So therefore, x is equal to a negative 4. So when I want to say 3 raised to what number equals an 81, that's just going to equal a negative 4. Okay, because again, that makes sense. Like 3 raised to the negative first power, you're going to put that in as a reciprocal, and it kind of works. In the second example, same kind of thing, same kind of idea. What we're going to want to do is make sure we write these with the same base. So, because again, this one makes sense why we're using a fraction or at least a negative number. Because when I have 64 raised to what number equals 4, well, how do you have something that's being raised to a power and it's going to go smaller in value? That's where negative powers come into play. So again, what we simply want to do here to be able to identify this is we want to go ahead and say, all right, well, 4 raised to what number equals x. Well, 4 squared is going to be 16. And if we multiply that 4 one more time, that's going to be 64. So there I can say 4 cubed, right, is equal to a 4. Now I can basically say, well, that's really a power to the 1, first power. Actually, not fraction. It's not a negative number. It's going to be fractions, right? Because now I can say that's going to be a 3x is equal to 1 and divide by 3 on both sides, and x is equal to a 1/3. So therefore, in this case, I can say that this answer is going to equal a 1/3, which again is kind of like taking the cube root, right? And because remember, we can rewrite a rational power as a radical. And so therefore, the cube root of 64 is indeed a 4. Okay, now in this example, we're basically going to use the rules of logarithm. So whenever you have a logarithm with the same base as its argument, right, then that's just going to equal 1. But if you have a logarithm with the same base and its argument raised to a power, then that's just going to equal the power. And there's a couple different ways we can verify that. We'll kind of explore again inside, through working through in the chapter on logarithms. But in this case, basically, you can just see that using these rules, my answer is going to be the power, which in this case is going to be an 8. Now, for solving logarithmic equations, there's a couple different things we want to do. The first thing we want to do is always make sure that we have a logarithm kind of isolated in this case. You can see I have a logarithm equal to a value. Now, to undo a logarithm, I need to use my inverse operations, right? So how do we undo a logarithm? So one way we could do it is rewrite this in exponential form, but the undo the logarithm would be to be able to exponentiate on both sides. So what I'm going to do is I'm basically going to have these be the powers with a base 8. So just like I did here, log base b of b raised to the x, the same thing works over here. If I have b raised to a log base b of x, that is also just going to equal an x, right? So when I have an exponent with the base raised to the logarithm of that same base of what the base of the exponent is, then it's just going to equal the argument of the logarithm. So by exponentiating on both sides, now what I'm going to go ahead and get is a 5x minus 11 is equal to an 8 squared, which is going to be a 64. Now I can just go ahead and add an 11 on both sides, and I get a 5x is going to equal to a 75, right? And so now I can just say how many times does 5 go into 75? So I can divide by 5 on both sides. And in this case, I'm going to get an x is going to equal a, let's see, that's going to be 5 goes into a 50. That's going to be 10 times, so that'd be a 15. Okay, now the other thing that's really important when we're solving logarithm equations is just to plug it in, like to make sure that it is going to make sense. So, if I plug this in, we want to make sure that it's still going to give us a value that would not be negative, because sometimes we will get extraneous solutions on logarithms. So, you can just go ahead and plug it in to make sure it's going to be verified. Now, in this example, I can't simplify my logarithm, or I can't exponentiate on both sides until I have exactly one single logarithm. So what I'm going to need to do in this case is actually use my rules of logarithms to condense this. So you remember when you have the difference of two logarithms, as long as they have the same base, you can go ahead and rewrite that as the quotient. So I can rewrite this as a log base 3 of a x plus 1 divided by an x minus 1. Okay, and that's going to now equal 4. Now you can see I can go ahead and exponentiate on both sides to kind of get rid of my logarithm. So therefore, I'll raise it to the base 3. And again, the reason why I want to choose the base 3 is because that's going to get rid of that logarithm, right? Because the logarithm is raised to it has a base of 3. Hence why I did the logarithm over here with a base 8. And so therefore, now I'll just have a x plus 1 divided by an x minus 1. And therefore, this is going to be a 3 raised to the 4th power. If you remember, that was going to be a 81, right? So that's going to be equal to 81. Now I need to solve for x. I have two x's, right? So I need to get the x off the denominator. So I'm going to multiply by x minus 1 here on both sides. And let's see what's that going to leave me with. That's going to leave me with an x plus 1 is going to equal to, let's go ahead and apply here some distributive property. So this is going to be an 81x and then minus 81. Okay, now what I'm simply going to do is to go ahead and solve. So therefore, I can add an 81 to both sides. I will subtract an x over here, and therefore I'm going to get an 82 is equal to an 80x. Now I can just go ahead and divide by 80 on both sides, and now what I'm going to get is a x is going to equal to, looks like I can reduce this by 2, so that's going to be a 41 over a 40. And again, the main thing is I want to make sure I can plug that in. It's not going to make either of my arguments negative. And you can see in this case that that is going to work. You could obviously go ahead and check it out to make sure, check it out to plug it in using a calculator. But the main thing is I just want to make sure both of my arguments are going to be positive. Therefore, I'm not going to have to worry about any extraneous solutions in that case. This example is going to be basically the exact same thing. When we have a logarithm, when we have the addition of two logarithms, then now what we can do is just go ahead and use that as a product. So I can rewrite this as a log base 2 of an x plus 2 times a x minus 5 equals 3, right? So now I can go ahead and exponentiate on both sides. So I'll raise these to base 2, and then I can multiply the binomials, x plus 2 times x minus 5. So that's going to be an x squared. Let's see, that's going to be a 2, so that'd be minus a 3x. Minus 10 is going to equal a 8. That is not an 8. Yeah, it's an 8. Then let's go ahead and subtract that over here. So now I have a x squared minus a 3x minus 18 is equal to 0. Okay, so now I want to be able to, I need to go ahead and factor this. What two numbers multiplied to give me negative 18, add to give me a negative 3. And that's going to be an x minus 6 times a x plus 3 is going to equal 0. Okay, and now I can use the zero product property. So by setting them both equal to 0, right? So x plus 3 is equal to 0. Just want to make sure, and therefore I get x equals 6 and x is equal to a negative 3. Okay, now one thing that's really important here is we want to make sure that none of these are going to make us have extraneous solutions, right? So I can plug in the 6 into both of those. That's going to work. And if I plug in a negative 3 though, notice when I plug in negative 3 minus 5 is a negative 8. 2 raised to what number equals a negative 8? That doesn't exist. So this is going to be an extraneous solution. So my only answer is going to be x equals 6. X equals negative 3 is an extraneous solution. So do you remember that one-to-one property that we talked about for exponential equations? Like if I have a to the x is equal to a to the y, then x is equal to y, right? That's the one-to-one property. That works for exponential equations. That also works for logarithm equations. So if I have a logarithm equal to a logarithm with the same base, in this case, they have the same base, which is both e, then you can simply just set the arguments equal to each other. So now I basically just have an 8 plus a 3x squared is equal to a 4x squared minus a 7x. So now I have a lovely quadratic equation that I just need to go ahead and set equal to 0 to go ahead and solve. So to do that, I will subtract a 3x squared on both sides, and I'll subtract an 8 on both sides. All right, so I get 0 equals a x squared, let's see, minus a 7x minus 8. And therefore now I can go ahead and factor this into an x minus an 8 and an x minus 1. Now I could go ahead and use the zero product property like I did up here, or hopefully you recognize here that I can determine that x is going to equal an 8 and x is going to equal a positive 1. Now what I simply want to do is go ahead and make sure that both of those are going to work, right? So when I plug them in, I want to make sure that my arguments for each logarithm are going to be positive. Well, obviously squaring both of them is going to be positive plus 8. That works. In this case, you know, when I do if I plug in a 8, negative 7 times 8 is going to be a 56, right? But when I square 8, that's 64. So 64, you know, minus the negative number, that's going to work. However, when I plug in 1, that gives me a negative 7. That gives me 4. So 4 minus 7 is negative 3. 1 is not going to work. So therefore, that answer is extraneous. Okay, so now let's move into exponential equations. And when we're focusing on exponential equations, the main thing that we're going to want to do in this case is just kind of make sure that we have the bases. We want to look for using our one-to-one properties. So in this case, what I'm simply going to do is just rewrite I want to be able to see how can I rewrite 8 and 32 with the same base. So to rewrite 8, what I can do is rewrite that as a 2 cubed raised to the x, and a 32, I can rewrite that as a 2 to the 5th power. Okay, now you can see that they have the same base. So now I can write the equation of 3x is going to equal 5, divide by 3, x is going to equal a 5/3. In this example, same thing I'm going to want to do. I'm going to want to rewrite the 16 as a negative number, or with a negative exponent, I'm sorry. So that's a 64 negative 2k is equal to a 16 to the negative 1st power. Okay, so now I want to see what numbers will they raise. Now, a lot of people will say 8, right? But yeah, 8 goes into 64 8 times, and 8 goes to 16 2 times, but that's not the same base, right? So we got to use them as a base. We got to use them with powers. So 64 can actually be written as 2 to the 6th power, and that's going to be times a negative 2, okay? And then 16 can be written as 2 to the 4th power. So that'd be 2 to the 4th power raised to the negative 1st power. And again, notice how I'm using my parentheses. Notice how I'm using my parentheses in this case. So therefore, we can make sure that we multiply those. So now I can just apply the one-to-one property. And what I'm going to get here is a negative 12k is equal to a negative 4. Okay, so divide by negative 12, divide by negative 12. And then in this case, k is going to equal to a positive 1/3. And yeah, that would definitely, that's going to make sense here as far as plugging that in. Now in this last example here, we have 5 raised to the n plus 3 plus 6 equals 97. So when I go ahead and subtract a 6, right, because just like the logarithms, how we want to isolate the logarithms or get it to one logarithm, the same thing we want to do for exponential equation. We want to isolate this. 5 to the n plus 3 is going to equal a 91. We want to isolate the exponent. So now we need to be able to do, well, how can I solve this? Like, how do I get the n plus 3 off of the numerator? Well, if you remember that, going back to that rule, if I have log base b of b raised to the x, like if I want to find out what's in that exponent, I need to, let me see. Yeah, if I have a b raised to x, if I take the logarithm of that, that's just going to equal an x. So basically what I want to do is take the logarithm of base 5 of both sides. So what that's going to now give me is a n plus 3 is equal to a log base 5 of 91. Now I can just subtract 3 on both sides, and n is going to equal to a log. Now in this case, a lot of calculators, you're not going to be able to type that in exactly how it is, right? So what I'd recommend you do here is go ahead and use the change of base formula. So I rewrite this as a log of 91 all over a log of 5, and then you're going to minus a 3. So in this case, now this is going to be a log base 10 on your calculator, rather than using the log of base 5 and 91. And I'm just going to go ahead and approximate this. Just make sure you are closing your parentheses when you're doing this. I'm going to plug this into my calculator and kind of see what I'm going to get. Minus 3, and that's going to give me a negative value, which again, negative 5 to the negative. Yeah, okay, that's going to make sense. Or at least that would work. And that I'm getting approximately negative 0.197, and I'll just round to the nearest thousandth in this case.